All right, I think we'll get started. Once again, thank you everyone for coming to today's drone seminar. And thank you, many of you, Scott, Robert, Fred, who are joining online. It's good to see many familiar faces here at the conference, at the talk. It's my distinct pleasure to introduce a good friend, Professor Ken Duffy. I just found out that he is the only person at Northeastern who was chair of EC department and also the math department. Wow, that's pretty impressive. I first met Ken in Paris, of all places, at International Symposium of Information Theory. And I was, I just had given a talk and I was trying to get something to eat in this French restaurant. I was trying to, I think, order a hamburger. And then, of course, I didn't speak French, so I didn't know what to do. And it's actually Ken happened to be in that restaurant with his wife. And he graciously helped me order my food. And I think you ended up inviting me to eat with you and Muriel. Right. And I think you ended up paying for me, too. So he's a very generous soul, and he's a great friend, but he's an amazing scholar and researcher and teacher, and now an administrator. So he has a lot riding on his shoulders, but he's going to talk to us about error correcting code, which is, whether you know it or not, you used it if you actually ever talk today on your phone, right? It's everywhere. So excited to hear about what Professor Duffy has to say about that. So please welcome Professor Ken Duffy.
Thank you very much. Thank you very much, Peter. I was quite worried about where that story was going. If it had just resulted in us paying the bill, that's okay. It could have been a lot worse. Thank you all for coming and for taking time out of your Friday afternoon to come to the talk. As Peter said, I have previously been interim chair of ECE, and now I'm the chair of mathematics. Whether you think that's a good thing or a bad thing or I'm a fool, I'll let you decide. It could be any of the three. The work I'm going to talk about today, for fear that I run out of time, I'm going to start with my acknowledgements first. And that means that at least the most important part of this talk from my point of view will happen. So everything I'm going to talk about today is done in collaboration with Muriel Medard, who's a chair professor at MIT. And the nature of this work is she and I started doing this maybe 7 or 8 years ago. And when we started doing it, we were like, okay, it started out as a piece of mathematics, it became algorithms, and then we knew everybody would say it would never work, right? So we started inventing these algorithms, and we knew people would say, look, it'll never work in practice. So very early on, we started collaborating with Rabia Yazicigil, who's now an associate tenured professor in Boston University. We started working with her when she took up her post as an assistant professor originally. And Rabia designed circuits. So the interesting thing perhaps about the topic I'm going to talk about today, as Peter said, is error correction. The nature of error correction is every single device you have does it. The second aspect that you may want to know about it is that it normally takes place in dedicated circuits. And the reason why that matters is that a lot of the common understanding you get about computational complexity from computer science courses and from those considerations don't really apply when you implement your algorithms and circuits. And so the reason that we started collaborating with Rabia was, we'd publish a paper, describe an algorithm, people would say it wouldn't work. We'd publish a chip that shows that it does it and is efficient. And then we'd come up with something new and people would say, you can't do that either and it won't be efficient, and we'd make another chip and so on. But it's been an awful lot of fun. And needless to say, at this stage, we've had the good fortune of being in receipt of research funding, and that means we've had a lot of fantastic postdocs and students collaborate in this work. But given that it's a Friday afternoon, I thought I would start off with a little bit of philosophy, particularly given, as Peter said, I have a joint appointment between math and ECE. I don't know if people know that in America, up until the 1940s or 50s, you couldn't be a probabilist in a math department. Probability was something that you did on the side. It wasn't a serious subject, which is kind of interesting because in Hilbert's address to the International Congress of Mathematics in 1900, one of the open problems that he said should be solved in the following century was the axiomatic treatment of probability. So the two first identifiable sole probabilists in America were these two guys, William Feller and Joe Doob. There's one story that you may know about them, which I'm going to retell, but don't worry, there'll be another one that you probably won't have heard. So the story about these two is they both wrote a very influential books in probability in the 1940s/1950s. And the two of them are very distinct style of mathematicians. So from my point of view, Willie Feller was one of those kind of Olympiad-style mathematicians. You give him a problem, and he will find the best technique for that particular problem, and he had this infinite bag of techniques. Whereas Joe Doob was more like a structural mathematician, one of these people who likes seeing, a design from the get-go that you build and build on. So the two of them wrote books that are very, very different, both of which are very influential. And they agreed that one thing that their books had to agree on was the fundamental object in probability theory, the name of it. So I guess everybody in the room is familiar with the concept of a random variable. If anybody is unfamiliar, please leave the room. I'm joking. So actually, William asserted that everybody in the field called that thing a random variable. And Joseph asserted that everybody in that field called it a chance variable. The two have very, very different connotations. What are the chances of something happening versus something random? But they did agree that their books had to agree on the terminology. So does anybody want to guess how they settled that decision? They coin flipped, and we got stuck with random variable, and there's a generation of students who don't fully understand probability theory. Okay, but Joe enters our story again in a minute. The core of what I'm going to talk about stems from a beautiful paper that Claude Shannon wrote in the 1940s. The history of Shannon is itself absolutely remarkable. That first paper coins the word bit for binary digit. It's the first paper in which it occurs. And if you ever visited Boston, his grave is in Cambridge, so you can go and visit it. I can see my pop quiz is not going to work very well today. Do people know what's on Boltzmann's grave? Obviously, I need to be in a physics department to tell this talk. S is K log W. Very good. Right, so he gets 2 points. So Boltzmann's grave has Boltzmann's formula, which is the entropy formula on it. It's kind of complicated. Boltzmann never wrote that formula, but that's a separate story. People want to guess what's on the back of Shannon's grave? So on the back of Shannon's grave, you have Shannon entropy. This is a picture I took a couple of weeks ago. So now you have added motivation to go and have a look. Okay. But before we move to the heavier stuff, I don't know if people know, because again, it's an engineering school, and you're all much younger and have longer in your life to go than me. In mathematics, unlike other fields, you're used to getting anonymous reviews for your papers and that being frustrating. One of the things that happens in mathematics is that happens too. But after the fact, reviews are written that are not anonymous. And so the American Math Society publishes these things called mathematical reviews. And they're kind of synopsises of papers. And when I was a young person, I would read them because you couldn't go and get a copy of every journal article. You used to get a compendium of these reviews, and then you would be able to read them to see what people thought were in them. But Joe Doob wrote the mathematical review for Shannon's incredible paper. So this is also a somewhat known story. And in it, most of the review is quite reasonable, but kind of in a pre-internet flame. He ends the review with, the discussion is suggestive throughout rather than mathematical. And it's not always clear that the author's mathematical intentions are honorable. Okay. Which apparently really, really upset Shannon. Now, I heard conflicting stories. I heard Doob regretted it later in life, but I recently met someone who knew him well who said, no, he never regretted it at all. So, okay. Jury's out. But the funny thing is, this story is somewhat known. But at some stage I was thinking, well, I wonder if Joe Doob wrote nasty reviews about anything else either, so I started going on. So, I'm pretty sure that Shannon's intentions were honorable. But his program in that paper was made more rigorous slightly later by a guy called Macmillan, and it turns out that Joe Doob wrote the review of Macmillan's paper as well. And in amongst all of the rest of the nice stuff ends with, following the tradition, the detailed epsilontics of the proof of the fundamental theorem are admitted, and also a slight. The upside of that for me is that following the tradition, I'm not going to give you any details of any of my proofs. Right? So in the rest of the talk, everything I will say will be suggestive, and you can judge for yourself whether my intentions are honorable. Right? I'll run out of time if I tell all my funny stories, but it's worth going and reading a review of a much later paper by Brockway, which is also very funny. Okay. So the subject of the talk is forward error correction, which, as Peter said, is universal. And it dates back to Shannon's paper in 1948, which is pretty remarkable given that digital information was not an obvious thing. People may know the history. He had studied philosophy in part as an undergraduate and had learned about Boolean logic, which was, of course, invented in order to form a rigorous form of logical arguments. But the basic premise of forward error correction is that when I send you data, whether it's stored or communicated, there's a risk that it'll become corrupted. So bits will be flipped. And if it was a case that every string had meaning, every string of bits had meaning, if it's corrupted along the way, you'll never know. And so the idea is you have to thin out the space. So I have to create a code book, which is, we'll just talk about binary for today, but for all strings of length n, as opposed to all 2 to the n strings having meaning, only a subset of them, 2 to the k, will have meaning. Right? And such codes are called rate k over n, because for every, in the long run, for every n bits you get k of value, basically. And the idea of forward error correction then is if you receive a string and it's not in your code book, then something corrupt happened. And what forward error correction is trying to do is trying to say, okay, given I received something that's not in my code book, what was the most likely thing to have been sent? Right? So that's the objective. And forward error correction is ubiquitous. Absolutely every single device you have does it. Shannon's original beautiful work is very elegant. It's non-constructive. It basically shows that the densest rate, so that the highest rate that you can push information through a system depends on a statistic of the corruption that we now call Shannon entropy. There's a story about why he called it entropy, but again, I'll run out of time if I tell you that. He also proved in that paper that if you have a code of a given rate, so a given k over n, then you're better off letting n be as long as possible. So that's also, see, and the nature of the proof is non-constructive. He doesn't actually tell you how to construct a code book. The reason why that works is he basically proves if you pick a code at random, it's highly likely to be good, and therefore I can study the ensemble of all code books. And so he doesn't do that, and he actually doesn't give you a useful decoder either. But basically, you can still abstractly prove, limits of what's the best you can do. Now, in his original consideration, he constructed the code at random. So out of the 2 to the n strings, you pick 2 to the k of them, and you just form a book. And that's completely impractical, right? Because for any reasonable length of k, your unstructured data will be this absolutely enormous database. So that problem was resolved very rapidly. If you want to think of his original codes as being a completely unstructured language, the codes that we use now are like ones with a perfect grammar. So the way that works is pretty much everything in your devices, with a little bit of nuance. You give me k bits, and I describe a single matrix. And I take your k bits, and I multiply it by this single matrix to give you a string of n bits. And what the multiplication is in, for all of the devices you have in front of you, is all in F2. So it's all in binary. Right? So if you want to think about the idea, what do? You're going to give me k bits, and I want to give you some additional redundant information. So what I'm going to do is I'm going to give you an extra n minus k bits, and what they are is essentially just linear equations of the original k bits. Right? So for example, I might give you an overall parity check. I might give you a parity of the first half of the data, the parity of the second half of the data. And the advantage of that is you describe the entire code structure just with that simple matrix, right? Which, you know, even naively looks like a K by N matrix, which is much, much smaller than my big code book. So the storage problem is resolved very early on, but there's a difficulty. In the 1970s, Berlekamp, McAleese, and Van Tilburg proved that decoding, so if I give you a string of bits and I give you no side information, and you go, okay, I had a look at it and the equations don't work, it's not in my code book. And I say, okay, well, find me the nearest code word in Hamming distance, the smallest number of bit flips that will find me a code word. They proved that doing so was an NP-complete problem. It means that there's a sequence of codes for which the complexity of doing that is growing exponentially. It means any hope of creating a universal algorithm that, regardless of the code structure, that for any G can do this in an efficient way is not possible. Right? People still with me? Okay. So what that's done is it's led to the practical design at the moment. Normally the way people do things is we co-design encoders and decoders. So we co-design those G matrices so that I have something that can decode them. You know, for example, every piece of data you've ever sent anywhere, and even on your Bluetooth device, has a CRC attached. It's a little cyclic redundancy check code. There's typically not perceived to have a decoder, but it allows you to check for whether data is consistent or not, and if it's not consistent, you drop it. There's other ones for which we have efficient hard detection decoders. That means I give you the string of bits, but no side information. And then we have code books for which we have efficient soft detection decoders. Soft detection decoders are very significant and important. Soft detection is like you're listening to me in the room. I slur my speech or something goes past. You can kind of localize to where the error is, right? And so that localization information is super useful in decoding. Okay? And, you know, just for example, in your phone, there's 2 different codes and 2 different decoders used. Okay? So the thing I'm going to talk to you today is something that Muriel and I and Rabia have been developing for the past decade, and now a lot of other people too, called guessing random additive noise decoding. And the idea with GRAND was we're going to replace all of these chips, which are different chips for doing different decodings of different things. And we're going to replace them with a single chip. So you give me any code of any structure and I'm going to decode it for you. And in fact, that's an actual diamonograph of a chip, the first GRAND chip that we made. And the idea is that we're going to make a universal decoder, one that can solve these problems, that you give me a string. It's not in your code book, and I'm going to find you the thing that's in your code book. Okay. Now, at this stage, you may be remembering a very brilliant episode of The Simpsons where Lisa makes a perpetual motion machine, and it is declared by Homer that, you know, we obey the laws of thermodynamics. So a minute ago, I told you that what I've just described is not possible, right? So there must be some sort of caveat. I told you that we know that we can't produce a universal decoder for arbitrarily long codes. Okay, so we'll clarify that as we go along. But basically, the premise of the work is relatively straightforward. Normally, the way we think about decoding is, you know, xn here is the string that you've sent, nn describes the bits that were flipped, and yn is what you received. Normally what decoders do is they go, okay, I know the structure of the code book. I've received yn. I'll try and find a suitable xn. So you try and find a suitable code word. But if you told me the code word that was transmitted, you would have also simultaneously told me which bits were flipped and what I received. And so the idea is to solve the other problem. Rather than try and identify the thing that was transmitted, why don't we go looking for the thing for which bits were flipped? And that idea is very simple. It's amenable to mathematical analysis and actually amenable to very efficient implementation. So the idea, as I said, is if you receive something off the channel, then why don't you go look for what bits were flipped rather than try and use codebook structure? And in particular, the more you know about how the channel behaves, the more capable you are of doing that, the more efficiently. And I said these sort of algorithms, the reason why they're implemented in circuits is if you want to think of it this way, when I give you data and I encode it, I create extra equations of that data. And at the receiver, when it's corrupt, I need to kind of find a solution, and it's an integer style problem, right? And I need to find a solution that will resolve those equations, but I need to do it fast enough that it's transparent to the communication. And that's why we do it in circuits. We do it in kind of highly parallelized ways because it has to be faster than your data rate. And the thing is, the more corrupt your channel is, the more work you have to do to solve those problems. So that's why these things are made in chips. And in fact, these are 3 chips that we've typed out and published. But when we started doing this work, as I said, Muriel and I decided we would start making chips fairly early on to convince people that it was practical. Perhaps we didn't really need to do so because the circuits community figured out that it was implementable too, and now there's actually a huge big pile of other circuits for implementing our algorithms. But let me describe it to you in very basic terms, and we'll get on to the more interesting version of the problem. Okay. So what's the idea? The idea with something like Grand is that all I really need is I need the string that you're giving me, particularly if I have hard detection information, and a mechanism to check whether something is in the codebook. And if you have an ability to sequentially create bit flip sequences from most likely to least likely, the most likely thing is always whatever you read off the channel is correct. If you knew no other information, you'd probably imagine that the next most likely thing is a single bit flip somewhere, and so on. You can sequentially create those sequences. The first time, you invert that effect, and you check to see if what remains is in the codebook. The first time that you would find something that was in the codebook would be a maximum likelihood decoding. So if you can make those sequences in decreasing order of likelihood, so that becomes the challenge, then you will be able to, the first thing that you would find would indeed be a maximum likelihood decoding. It would be the best solution to the problem. And this really vanilla version that just encapsulates the idea, the reason why it can work with any codebook is all you're using the codebook as is effectively as a hash. It's like checking to see whether a problem is solved or not. Even if you had Shannon's original horrendous randomly constructed codebook, you could still actually do this efficiently because checking whether something is in an unstructured codebook is just a lookup. And if it's a linear codebook, then it just requires a single matrix multiplication in a binary field. And that's something we can do in a single clock cycle in a circuit. So the reason why this stuff is very efficient, and the reason why a lot of people in the circuits community jumped on it, was if we can make these sequences very efficiently, if we can make them in parallel and check codebook membership in parallel, we can all do these things in a hugely parallelized fashion. But, this work started out as a piece of mathematics, which I don't have the time to describe fully today, but I am the chair of the math department, so I feel I should mention it. This video is being recorded, and I might get lampooned when I return to Boston. There's a very beautiful piece of mathematics behind studying this algorithm in general, which maybe on an idle day you might want to go read, whether it's our paper or not, the original stuff. There's a general problem in information theory called guesswork. Guesswork is about you pick something from a distribution. I know the distribution. I want to identify what you've selected, and I can ask yes-no questions. But the yes-no questions I can only ask is like, did you pick 1? Did you pick 2? Did you pick 3? And guesswork is how many questions does it take me to identify what you selected from that distribution. And it has a history that goes back to about 1994, when the first question that was asked was, does Shannon entropy have anything to do with that problem? And it turned out that the answer was no, which is why it's, in part, why it's interesting as an information theory question. But here guesswork comes into it because effectively the problem I described was the channel has done something to your bits. It's flipped a certain number of them. I know something about your channel. I'm going to create sequences in decreasing order of likelihood, and therefore the number of queries it takes me to identify that is this guesswork. But in competition with it, when can things go wrong, I may make a certain number of queries, and then I'll identify something in the codebook that wasn't the thing you transmitted. And this is very pretty because it means understanding how this decoder works, which is exactly maximum likelihood decoding. So regardless of whether you like the algorithm or not, you can use this to prove your theorems in order to understand how often maximum likelihood decoding is correct. All you have to do is worry about the distribution of how often does it take fewer queries to identify the real thing that happened on the channel versus bumping into something erroneous in the codebook. And you can do an awful lot of stuff with it, and it unifies a bunch of very different papers, including very deep results that Bob Gallagher proved that I understand he could prove and could establish, but didn't really know why the structure was true. And if you look at it through this lens, it just becomes obvious. But the thing I wanted to talk about, given we're in the engineering department, is perhaps the more engineering side of what happens when things get fun. So the hard detection systems are like, you're reading data off your hard drive, or I send you an email and there's a typo on it, right? In some sense, the corruption occurs at some stage, not coinciding with you reading or observing the data. The soft detection one, which is every radio, every optical system, you have side information. Basically, when you receive a symbol, you not only receive what you think is the most likely thing to have been transmitted, you receive some uncertainty measure. So, if people have done comms courses, they'll be familiar that basically this is with every bit you get an LLR, a log likelihood ratio, a ratio between the likelihood that you believe it's a 0 and a 1. If you haven't seen it before and you're mathematically inclined, you might just imagine every bit I give you a number between 0 and a half, and I tell you this is the likelihood that I'm wrong. Right? So for every bit, you now not only know the most likely thing that came off the channel, which may not satisfy your codebook constraints, but you also have the side information. The question is, how do you use the side information to do the decoding? And there's theory that tells you there's a significant gain to be had, which makes sense, right? If I write a sentence and I give it to you and you try and find where the error is, it could be anywhere. If you hear me speaking and I throw in an Irish word at some stage, you can probably identify that that was the one you didn't understand. Okay, so the question is, how do you use soft detection information? I think that's the thing that's grabbed the community the most. And so the algorithm kind of in principle at a high level remains the same. What you're going to do is you're going to take this soft information as input, and now I want to still create sequences in order, binary bit flip sequences in order from most likely to least likely. But now you have to take the side information. It's like not every bit is equally likely to have been flipped. And this is a hard problem. It turns out you can write down an algorithm to do it that so far nobody has been able to implement in hardware efficiently. So you can do things with max heaps and stuff. You can make tree structures. It's a lot of fun. And in software, you can implement it, and that's great because it's actually a soft detection maximum likelihood decoder. It tells you you will never make a better decoding than this, so you can implement it and have a go, and it gives you an outer bound of how good things are. But there's no way, at least to date, I have a paper to review, so we'll see. To date, nobody has made an efficient hardware implementation of it. A number of years ago, we introduced an algorithm called OrbGrand for ordered reliability bits grand, which I'll try and explain now, which approximates the solution of this problem and has been very implementable in hardware, and now there are multiple circuits and more than one chip that do so. And it's fun for a bunch of reasons. One is that it starts with knowing something about philosophy of statistics, knowing something about what looks like hard problems in discrete maths called integer partition problems, and all of this stuff flukily coming together into something that can be very implemented in a circuit. So I'm going to try and explain that a bit. Okay. And actually, there's been other work by other teams proving that the algorithm is asymptotically as good as you can get. Okay. So let me try and explain the premise of the algorithm. what we want to do is, unlike the original thing, like if I have no side information, I think every bit is equally likely to be flipped, I follow Hamming weight, then what happens here is like I have a sequence, and each bit is likely to be flipped with a different probability. So for each bit I give you a bit flip probability pi. Then what I can do is I can say the likelihood of a sequence of bit flips, and I'm just going to write it this way. I'm going to say it's likelihood that nothing is flipped, and then the ones that you want to flip, I'm going to swap out the 1 minus p, which is they haven't been flipped, with a p that they have. And why would I want to do that? The reason why I want to do it is the term at the front is common to all of those sequences, and that thing is proportional to e to the minus the sum of these log likelihood ratios. So what I want to do is I want to find an algorithm that will create these sequences in decreasing order of likelihood, and in order to do so, what I really need to do is create them in increasing order of the sum of their log likelihood ratios. So that's my task. But the problem is, even if you take the prototypical toy channel that we teach in class, and I put 500 bits through it, and I calculate in a normal soft detection system, what's the likelihood that the bit is being flipped? You'll get all this scatter plot. So this is the information that I'm giving you. I'm saying bit 50 has whatever 0.1 likelihood of being wrong, and I'm going to ask you, go and create sequences from most likely to least likely. And it looks like there's no structure. But if you rank order those, so if I just take those datum and I rank order them, so I take the smallest and I put it in position 1, the second smallest in position 2, and I do 10 independent realizations of that, they all look like this. The structure arises. This is too big a room to ask the question, have people seen this sort of thing before? Probably everybody in the room knows that if I give you independent observations from a random variable and you calculate the empirical cumulative distribution function, then eventually it will converge to the CDF. The exact same thing happens if you rank order things. You get this structure arises just through rank ordering. And so there is clearly some structure in here, and the consistency arises for the same reasons that eCDFs converge. So now the fun is, we started with a math hat, we took it off. Now we're going to put on a stats hat. So when you see this, what do you see if you're a statistician? Okay. So in a previous life, I directed a large applied maths research institute, and I hired a very senior statistician, and I had a lot of very confusing conversations with him, because it occurred to me we had a difference in language, that for me, a model was something that described microscopic behavior that I extrapolated to macroscopic. And for him, it was phenomenological. If I showed him this data, he would say it's a line, right? So he'd say a line through the origin. So often in statistics, they're phenomenological descriptions. So it turns out that in noisy channel conditions, these reliabilities always have to look like this. You can prove a general theorem that's very broad that says this is the phenomenology that you will get. If that was the phenomenology that you would get, you can now ask the question, if likelihood ratios, if these log likelihood ratios followed a line, how should I make those patterns? And if you follow a very simple line of argument, something fun happens. So if I rank order these likelihood ratios from least likely to most likely, and I assume they're aligned through the origin, and I just follow the logic, then if every bit was equally likely to be flipped, then the likelihood of a particular sequence would be, it would be decreasing in how many bits you wanted to flip. Here, if the log likelihood ratios follow a line, it turns out that instead the cost function associated with it is, if you want to flip the least reliable bit, that will cost you 1. If you want to flip the second least reliable bit, it will cost you 2. If you want to flip the third least reliable bit, it will cost you 3. Or to the point, if you want to flip the third least reliable bit, that will cost you 3. But flipping the least and second least reliable bit will cost you 1 plus 2, which is also 3. They're equally likely in this model. So it turns out that if this was true, if these likelihoods really did follow a line, then you could create these patterns by solving something that's called an integer partition problem, which looks like it's kind of scary, but isn't. So what is this telling you? It's telling you that the slope of the line didn't matter. So regardless of what the slope is, I don't even need to know it. It's a bit like in a hard detection channel, I don't need to know what the bit flip probability is to know that adding an extra bit flip is less likely. So I don't need to know what the slope is. And if the model was correct, so if your things really were along a line, I'd actually generate maximum likelihood decodings. So I'm not going to describe the algorithm that generates these, but for the decoder's purpose, what it means is that to create an efficient version of this decoder, you only need to take the bits that you get off the channel, tell me which is the bit you trust the least, which is the bit you trust the second least, which is the bit you trust the third least, and so on. And once you do that, the sequence of patterns that I should query is deterministic. And it looks like the thing in front of you, which is something that you can mathematically study on its own, right? But it means that this is why the algorithm is so implementable. And I won't describe it, but it turns out that this integer partition problem, which normally as a mathematician I'd be scared by, it turns out that we can create a very simple circuit that can create these patterns once in a clock cycle and check code book membership all without a bother. And it's really very pretty. So let me tell you a little bit about what we can do with it. So here's an illustration of something where there's a code in your phone. So all of the data, there's two different codes in your phone. If you've got a 5G phone, one for your data and one for your control communications. So this is one associated with control packets. And this is a standard representation of how good a decoder is. On the x-axis, I have something related to signal-to-noise ratio. So the channel's getting cleaner as I move further right. And on the vertical axis, I'm showing you what's the proportion of decodings that are in error. That light green line is the algorithm that your phone is using at the moment for this code. And the lines to the left of it are this algorithm that I just described to you. So if we, apart from the red one, so the red one is the optimal one that don't have an efficient implementation for in hardware, but tells us what the outside performance bound would be. And the other lines are telling you what this decoder would do. So basically, in noisier channel conditions, it is getting the answer right more often. But there's also all sorts of other fun things. This was, to all extents and purposes, the first decoder that could decode any code. So we could start going and asking, how much does code structure matter to your performance? And actually, there's a very pretty theoretical paper in 1990 that says every code you cannot think of is good. It's kind of why Shannon's theorem works in the first place. Codes are not special, decoders are. And so here what this plot is showing you, two lines on the right, never mind, they're to do with what happens if you do hard detection decoding. Thing on the left are the soft detection decoders. They're showing you how much gain you get from having this side information. But the codes that are in there are everything from the thing that's in your phone to a single code picked at random to a cyclic redundancy check code that all of your devices are using but we don't normally use to decode, and even a nonlinear code created from a cryptographic function. And they all essentially perform the same. I've got about 7 minutes. Okay, so this part of the story, and it's somewhat condensed, translated into a chip, tells you that we basically have this chip, you can load any code onto it and it will decode it. But of course, there has to be some limitation, or I've broken the laws of thermodynamics. The limitation is that the code can't have too much redundancy. But that's going to be okay for a reason I'm going to describe in a minute. Very busy slide, apologies for that. These decoders I've just described are called soft input. Right? So I get beliefs from the channel, I feed them into the decoder, and it helps me find what my solution should be. A soft output decoder in an ideal world, when I solve the puzzle, I'll tell you, okay, this is what you received from the channel. It wasn't in the code book. Here's the thing that I think it probably was. and I'm 92.7% sure that it's correct. Like an ideal one, I'd be able to give you this kind of confidence measure. And this is something that Dave Forney studied back in the 60s. And the problem is, I can't do that, right? So the problem is, in order for me to give you that confidence measure, what I really should be able to do is I'd have to take what you received, compare everything that's in the code book, say, what's the likelihood I received this, given this was given I sent this, that, the other. And, for the same reason that I can't do that brute force enumeration, I can't do this here either. And so there's a historic approximation, which is everything that people have used since the 60s up until 2 years ago, and without describing the derivation, which is actually really very straightforward. It's basically an application of Bayes' theorem, but it comes back to that notion of if we look at the decoder as the race between two different processes, how many queries to get the right answer and how many queries to get the wrong, that's not the way people have been thinking about it before. And you can ask the question, okay, given it took me this many queries to find something in the code book, what's the likelihood that it was one or the other, that it was the right one or the wrong one? And through a little bit of miraculousness, it turns out calculating those probabilities, even in the soft input case, is something we can do trivially. There is a little bit of a hint of magic. At some stage, we throw an approximation where I'm sure it looks obtuse if you go read the papers, but something is bound to be a geometric random variable for reasons I'm not going to explain. It's really quite curious because prior to this work, we first published it in like December 2023, there was no decoder that with a single code word could give you a confidence measure. And we've now gone back and discovered actually some other decoders could by considering them as if they were executing our algorithm. They're not executing our algorithm, but if we consider them as we could do the accounting as if they were executing our algorithm, get it? Okay. Why does it matter? I'm just going to tell you it's straightforward. Okay. Let me tell you why it might matter. So, soft output decoding, you can do all sorts of magical things with, because in general, I solve a puzzle for you and I give you an answer, but you don't want to use it if it's wrong, right? So if I give you like, oh, I'm only 10% sure it's right, then you throw it away, right? So there's good reasons why you might want to do it. But probably one of the most pertinent ones, at least in a short, not short, but in a single talk, is iterative decoding. I said we're in this position where any code that doesn't have too much redundancy, we can decode it very efficiently, and we've proved it in hardware, and other people have too. But perhaps one of the most interesting things is, since the very earliest days of error correction decoding, one of the primary quests is how do you design very long codes, right? Because Shannon has told us long codes are where the best bang per buck is, right? And there's a series of work, and loads of these things, perhaps not the younger people, the older professors in the audience, it has influenced your life because turbo codes went into 3G and 5G, some of these things are later and so on. I really like one of the things that Dave Forney did, which ended up on Voyager, right? So the Voyager satellites, they have, or probes have them. But the standard device is, if you want to think of it this way, I want to send you a big, long mathematical problem. And how do you solve big mathematical problems? You break them into chunks, right? And so actually, pretty much every long, powerful code is made by taking smaller codes and concatenating them into a longer one. So I make a big puzzle out of a small one, and then the solution, how do I go about and solve them, is I look at each part of the puzzle on its own. So I take a little part of the puzzle, I take the beliefs that I have, I push them through the puzzle, and then what I have to do is I have to update my beliefs afterwards. What happened was this part of the code didn't work out, so maybe it was these other bits. What do I believe now? I feed them into another part of the puzzle and I work around iteratively. So the long codes on your phone, LDPCs, which were invented by Muriel's PhD advisor in his thesis, Bob Gallagher, in the 60s, and were then lost, rediscovered in the 90s, when eventually computing power got to the stage where they could adapt them. They are constructed that way, for example. Bob was really ahead of his time. So your TV standards, the data channel on your phone, all uses these things. Bob's clever idea was he's going to make a big, long puzzle out of the simplest code possible, single parity checks, right? So his code is these little single parity checks. So we invent this decoder and we actually prove later on, oh, hang on a second, we can decode codes that have multiple parity checks rather than single ones, and we can get efficient soft output out of them. Why don't we go and try and decode some long codes? And the first thing we thought about, well, is, okay, what's the simplest structure we can do? Well, Bob came up with these things. Why don't we go to a code structure that Bob's PhD advisor, Muriel's PhD advisor's PhD advisor, came up with called product codes. These things are used in optics, by the way, already. So product codes, you have a single little code, a code that takes k bits and extends it to n. What you do is you take k squared of them and you write it in a k by k matrix. And what you do is you encode every row and then you encode every column. And so you go from having a code that takes k bits to n to having a code that takes k squared bits to n squared bits. Code rate drops, the code becomes much longer. These are the reason why they're used in optics is they're very desirable because to encode them, I can do all the rows in parallel, I can do all the columns in parallel. There's a lot of natural parallelism which reduces latency. And we just so you know, whether you go rows and columns or columns and rows, it doesn't matter. And we decided we would just go and look at these things. They're the simplest structure we could do. And we took the best decoder kind of before us would have been the outer blue line. And the thing that's in your phone is the cyan line. So again, it's like on the x-axis, it's a measure of how noisy the channel is going right. It's cleaner. And on the vertical axis is the fraction of packets that are in error. What you see is the product code decoded with our decoder does as well as the thing that's in your phone. Now at this stage you go, oh, well, you've cherry-picked. You've selected one example where you do as well. And that is true. It's something that we've done because normally we do better. Actually, that's an unusual example where we do as well, but normally we actually do better, which is what this thing is here on the left. This is just another code, again, one that's in your phone. Has hugely more redundant bits than we can manage on itself. And what happens is we're getting better performance from these codes that are even older, that have these very highly desirable iterative parallelizability. And the thing on the right is showing you, because the LDPCs in your phone, because the codes are so weak, they need a lot of iterations to solve the problem. These ones, you need much fewer iterations. So like all of these things, I can show you more examples. People have said, you know, we're not going to be able to do it efficiently in hardware. And so I don't have a picture of the chip up here for reasons I can explain some other time. In the circuits world, until the chip is published, I'm not allowed to show it to anybody. Okay. But needless to say, given every other algorithm we've come up with that people have said we haven't been able to build, we've gone and designed a chip, and then you go and measure it and prove that it's efficient. And so these iterative decodings, which is just one example of what you can do from this stuff, we're also in the process of building with Chips and Science Act money, and we're very confident that we'll be able to outperform the codes that are used in your phone. Okay. But I'm going to try and wrap up because I've got 50 minutes. So this is only one vein of thought on this process. It began with the idea, the very simple idea, that when you solve an error correction problem, you know not only what was transmitted, if you solve it correctly, but also what the channel did to your data. And starting with that premise, you can do all sorts of other things. You can start saying, well, the more I know about what the channel did, the better I can do. The reason why in error correction decoding, we assume that bits are flipped independently is that they're not on channels, but because the decoders are going to assume it, we artificially engineer the system so the errors that are in bursts get separated. Shannon tells you that's the wrong thing to do. If you calculate the entropy of the noise, if it's bursty, it has lower entropy. It's easier to identify because where the errors are co-located. So stealing ideas from thermodynamic probability theory, we've actually made a chip, this last of these chips, can decode in channels that have burst errors. And not only does it more efficiently, it improves the performance. But there's all sorts of fun things you can do with it. And even now, there's a lot of mathematical stuff to be done too. But we keep a web page over at MIT if you want to read more about it. But I'm just going to close. I appreciate, in hindsight, it was only when I got here I realized I called the talk modern developments in error correction. I should have put in biased modern developments, right? So the ones that we've been involved in that I appreciate. Well, I hope what I've tried to explain to you today is, we have this algorithm that lends itself not only to mathematical analysis, and in fact there are people in information theory proving theorems beyond us as well, but it's also people developing algorithms, and there's people developing circuits. And the reason for that is it's kind of a fresh look on an old problem that turns out to reveal an awful lot of opportunities. And if you'd like to read more, we keep a large collection of papers that you're welcome to go and read. And with that, I think I'll close so that I'm on time.